So in the last video, we talked about stationary versus non-stationary time series, and one way to go from a non-stationary time series to a stationary time series is to difference the time series. So for example, in this graph, you see the Google stock price in 2018, and this appears to be non-stationary because it doesn't appear to be roughly horizontal over time or display constant variance. And if you take a look at a snapshot at any given point in time, it doesn't look the same as if you were to look at another snapshot in time. So for modeling purposes, for ARIMA models, we do require a stationary time series. And for that, we need to use the differencing technique, which is to look at observations, the change in observations that are subsequent. So for the Google stock price, we can take a look at the difference data, which is the change in the Google closing stock price for 2018, and this data looks roughly horizontal. Differencing typically helps to stabilize the mean of the time series, which is what we require for ARIMA models. What it does is it removes the changes in the level of a time series, and therefore it eliminates, mostly it eliminates, but it also reduces the trends and seasonal components that are associated with that time series. So the difference series is really just the change between each observation in the original series. So if you were looking at the change, this is just, the value yt at time t minus the value at t minus 1. So you would have another time series, which is your differenced time series. And that difference time series would only have t minus 1 values because you don't have a possible value for the first observation. Now, typically in economics and finance, we're good if we would difference the data once and we would ultimately get a stationary time series, but sometimes we may require a higher order differencing. So for example, we may need second order differencing, which is to take the difference of the difference time series. So where is this used? This is usually done with exchange rate data or some other type of financial data sometimes, where your second order differencing is you take the change in yt and then you subtract off the change in yt minus 1. So if you open it up, this is yt minus 1, then you're subtracting off the change in yt minus 1, which is, if you open that up, that's yt minus 1 minus yt minus 2. You solve for this and you get yt minus 2 yt minus 1 plus yt minus 2. So this is just simple algebra. And the second order difference series is going to have t minus 2 values because you're not going to have the first two values in the series. So usually, by the time we have done second order differencing, we don't require any more differencing to make the data stationary, so we're good to go. But most often, we only require first order differencing. We also have a technique called seasonal differencing, which is just looking at the difference between an observation and the corresponding observation from the previous year. So you have, if you were looking at a seasonal difference for monthly data, for example, then you would have, the value would be January of 2020 minus January of 2019. And February of 2020 minus the value at February of 2019. So you would have these values that are corresponding to the same seasonal period from the previous year. Okay, so let's try to think about what that translates into. When we're seasonally differencing the time series, then the change in yt can be written as yt. So what is the value of the time series, let's say in January of 2020, minus what was the value of the time series in the previous year in January. okay, where M would represent the number of seasons. So if you had monthly data, this is YT minus 12. And similarly, you could expand this for, you could again take this to quarterly data where M is equal to 4, and so on and so forth. So let's take a look at an example here. We have the electricity production in the United States, which is in your US monthly electricity data set. You can plot this. This looks like the seasonal periods display sort of this multiplicative behavior over time. And what we can do sometimes to stabilize that variation is to take the log of the series. So take a look, when we take the logs, this starts looking, those peaks and troughs start looking roughly horizontal, roughly the same in magnitude. And what we still have here is an underlying trend in the data. Now, if we were to difference the time series, so if you want to go from this to making the series roughly horizontal, because this is monthly data, then we can difference the time series in such a way. So we can take the log, and then we can difference the time series using the difference command. And we can say difference it, so seasonally difference it. So when we say 12, we are putting 12 to say that, we're going to construct the changes as follows. We're going to take January of 2020, or January of 2010 minus January of 2009, and so on and so forth. Okay, so if you have quarterly data, then you would put 4 over here. Okay, so what you do get here, because we are manipulating the series first, we're taking logs and then we're taking the difference. If you look at the log difference, then you really just have the annual change or the percentage change in annual terms for electricity consumption, or production in this case, I'm sorry. So again, look how the data has transformed, and this looks roughly horizontal, but there is a difference in variability over time. So maybe these are periods of low volatility or low variability, but these are periods of high variability. So not completely stationary, but we have tests to see that. But let's say we want to go from this data, which is not looking stationary, to and then again we want to difference the time series. We can do that by using the pipe function on the seasonally differenced data by using the difference command on it. And this time, because we are not putting 12 or anything here, this is just looking at the difference between the subsequent values. And so the data becomes, looks roughly horizontal. We see these kind of outlying observations here, but those are just outlying. Mostly the data looks pretty horizontal. Now, the seasonally difference data is closer to being stationary. Why am I saying this? If you just took the difference of the original data, that would not look as stationary as the seasonally differenced series. So what we've done is we've done seasonal differencing first on the data, and then done first differencing. Okay, so this is the format you want to always follow, because a lot of times removing the seasonality can make the data look stationary or make it stationary. So whenever you're trying to apply both types of differencing, one is between subsequent observations, which is your regular first differencing, and the other is seasonal differencing, which is between the observation today minus the observation from last year in the same seasonal period. We always try to do seasonal differencing first, and then do first differencing. Okay, even though the result is pretty much going to be the same, sometimes you don't want to over difference the data. If seasonal differencing suffices, you want to keep it at that. The most important thing is you want to make sure that when differencing is used, when you're trying to forecast the data, whatever, um, however you've transformed your y-axis is sort of interpretable. So you don't want to lose that interpretability when you're differencing. So just to wrap up here, the interpretation of differencing is that when we're taking the first differences, we are looking at the change between one observation and the next. And when we are looking at seasonal differences, then we are looking at the change between 1 year to the next. So if you sort of difference your data 3 times for annual observations, the model is not going to be easily interpreted. Okay, so you want to make sure you want to be careful of that. So in the next video, we're going to be talking about some sophisticated tests that tell us about whether our data are stationary or not.